Let me welcome you to the first of the NCSA Directors Seminars for this new academic year. Delighted to see all of you here. We're also delighted to welcome Professor Amit Seth from Wright State University. Danny and I had a delightful hour talking with Professor this morning about a number of topics, and it's very clear there's a lot of overlap between his interest and the interest of the center that he runs at Wright State and many of the activities that are going on at NCSA. Our speaker is a very distinguished educator, researcher, and entrepreneur. He is the LexisNexis Ohio Eminent Scholar at Wright State University. He also directs this institute called Ubiquitous. It's an Ohio Center of Excellence in Knowledge-Enabled Computing. He's going to talk with us today about a number of the activities that he has ongoing in Ubiquitous. He is also an IEEE Fellow and is one of the most highly cited scholars in computer science. He's editor-in-chief of a number, or co-editor-in-chief of a number of journals, and he has founded and successfully managed 2 companies. So we are delighted to have Professor Seth here to tell us about the activities going on at Wright State.
Very much appreciate it. Delighted to have this opportunity to come and talk to you. I'm going to take first 2 minutes to introduce our center. It became Ohio Center of Excellence earlier this year, very briefly speaking, we take from the importance of knowledge, been well recognized, but in the context of new computing and communication arena, we have new opportunities. And our vision is, there's a longer version of it, but simply put, going from information to meaning. Today there is no dearth of data. There is huge amount of data in any field that you can think of. You at NCSA deal with very, very large amount of data and its processing. But I think there are still a lot of interesting challenges and opportunities as we abstract away from the raw data to what it means to humans. At the center we are 15 faculty, majority in computer science, but a number of them from cognitive science or psychology, biomedical sciences, healthcare, and business. So it's an interdisciplinary center, and one of the, I think, very interesting part of it is that we have been doing successfully a good bit of interdisciplinary work, and many of our activities are also with outside institutions. This is Joshi Center where we are housed. There are 13, 14 laboratories in the center, a number of local collaborations, especially with the Wright-Patterson Air Force Base, which is nearby, number of national collaborations, and many of them are funded, a number of international collaborations. We are an official member of World Wide Web Consortium, and our students travel at many places and do the internships and interact in significant ways. Well, reasonably funded, 45 or so PhD students and postdocs. Interesting that our thing in the Midwest has funding from Microsoft Research, IBM Research, HP Labs, Google, of course NSF, NIH, AFR, and things of that nature. Colleagues are well cited with over 2,000 citations on average, which is significant. And some of the colleagues had very well-known papers. We've been able to attract very high-quality faculty. Somebody we hired recently as an assistant professor with 100+ publications and editor-in-chief of journals and such. And have entrepreneurial relationship. One thing that I'm particularly proud of is that our students are very successful. They've done very, very well. Satya Sahu, and as I was talking very interestingly, he became tenure track faculty at Case Western in School of Medicine. So that's an interesting, I think, exemplar of how we can do interdisciplinary work. Meena joined IBM Urban Research. She was also NSF-CI Fellows. The other thing is that they work with a lot of companies and get a lot of good background before they get out. So here is my talk title, Computing for Human Experience. Semantics Empowered Sensors, Services, and Social Computing on Ubiquitous Web. Perhaps I won't get a lot of time to talk about our work in biomedical and health informatics arena as part of this talk. I thought I'll just mention that since there is a good bit of work there going on in those areas here, so perhaps we may have a chance to talk about them later on. One slide introduction to those among you who might be skeptical about semantics and in semantic web. I've been working with semantics for a long time, and that seems natural to me. I did meet people here who've been working with ideas related to metadata and RDF for a long period of time. So clearly there are no people here who know the value of metadata and semantics for quite some time. And in case there are not, there are others who are not, lately there is quite a bit of progress in this area in terms of not just recognition of the importance, but actual adoption and actual usage. Microsoft earlier this year purchased, 2 years ago purchased PowerSet. In fact, you can start to see importance of how that has happened. Bing, help Bing. If you see beta.bing.com, and I'll say a little bit later on. Earlier this year, Apple purchased Siri, a semantic web company. Google bought a MetaWeb. There's a big thing going on called Web of Data or Link Open Data Cloud. And then many of them are publishing data in graphical and RDF and other forms. Many of them are grappling with technological challenges of dealing with billions and trillions of triples in RDF. So that's another interesting thing that is going on. Perhaps we are the largest, maybe second largest US academic group in the semantic web in terms of number of faculty and students. Something that comes to my mind to show how it takes a decade or so for technology to evolve, I want to show you something interesting. This is a little snippet of a patent that we were awarded a decade ago. This is the basis for our company, the second company that I had founded. It was way early, too premature. Although technology that we developed still lives on, it was acquired 4 or 5 different times, and then currently it lives on and has products in some of the major banks in the world. In fact, majority of the major banks in the world have products that came out of this work. But you see on the left, in that figure 1 there, the domain models are being spec'd out. You'll see that Bing is actually has started to give you just that. And what's happening there is that behind each of the domains, whether you take entertainment and within that movie or sports or travel, that there is a large piece of background knowledge that all these companies are gathering. Yahoo calls it concept web or object web or concept based and object based. And I showed you the MetaWeb is, for example, a company that has very large amount of these public data sets that can be used in different domain. So those kind of background knowledge and informal forms of ontologies, you might call, are being leveraged to make better sense out of the data in that domain. Companies like Google have done exceptionally well in exploiting statistics and learning to the fullest. Now, in the next stage, I think we've gotten whatever we can get from that, more or less. But in the next stage, I think this background knowledge in semantics will play a very large role. And so you're starting to see that today. In 2000, I talked about some commercial applications. So clearly, after a decade, there are plenty of them. We can talk about it all day, but won't. So here is a pyramid talking about a whole bunch of whole bunch of technologies. And one way of looking at what Noesis does is that we provide the semantic core for interoperability, for integration, for better analytics, for better making sense of the data at each of these levels. in the thing. So while I won't talk about it, in the cloud computing arena, we use semantics related to data, functional semantics, non-functional semantics for interoperability. So a project called Cumulus has developed ways for building portable cloud applications that can be designed kind of once and deployed on the Amazon EC2 or Google App Engine or things of your choice. And another project does mobile cloud hybrid applications. Same way with web services, where we have our work became a W3C standard called SABISDL. And there we use again semantics to improve the interoperability, reusability of web services and such. The rest of the parts I'm going to talk about in the talk, so let's move on. Imagine when a farmer takes a consumer device that he has or she has and sees something unusual with the crop, takes a photograph with a tag or so, uploads to Farm Helper. Farm Helper has gets from the data that is conveyed to you or otherwise some metadata, location and time. Also with geocoding can pick up the satellite data, can pick up the weather data, and can also pick up the data related to soil survey, pest information, any of the other things that are out there, which is then all available for deciding what could be wrong with the crop, what can be done with the crop. And if that is not enough, there is access to 6 billion brains, well, currently more than 1 billion or so that are connected and on internet, and I think within the next few years, I think less than 5 years, there will be more than 2 billion brains, humans connected. So they can also be tapped. We have increasing number of technologies that give you instant access to the people both ways. So that would lead to essentially giving farmer what he or she wants. The point here is that you want to support a human in his very natural environment and with the minimal interaction with the system and with the minimum technological sophistication. That is the fundamental thing. And that's about your normal human experience and how computing can enhance that. So a number of people have before me have talked about a general theme and vision. I'm borrowing upon that and kind of seeing how we can realize now with the current advances. Here are some things. Mark Weiser, when he laid out, he wrote a very influential piece in Scientific American on computer for 21st century. His work became ubiquitous computing work, and that's not what I'm going to talk about. And that's not my emphasis. My emphasis is not how humans communicate with the computing. In fact, it is almost the reverse of it. So there are a number of things like that where technology disappears in the background and and actually takes care of what humans want in its very naturalistic conditions. So as a theme then, this computing for human experience will employ a suite of technologies to non-destructively and unobtrusively complement and enrich normal human activities with minimal explicit concern or effort on part of humans. So there are a bunch of features you can talk about: seamless, non-descriptive, unobtrusive, and so on and so forth. Anticipatory, knowledgeable, intelligent, implicit, ubiquitous, things of that nature. And in terms of technology, you have today mobile web, sensor web, social web, multimodal things all happening today. What is the integrative aspect of it? What is the glue? What is the one novel thing that brings all of them together to give significantly more advanced things to where the whole is lot more than the sum of its parts? A number of exciting visions that I have learned from, one of the most foremost being the work by the MEMEX engine that whenever Bush talked about in 1945 in the Atlantic Journal, as we may think, talks about trailblazing, how human brain thinks, and we latch onto a concept and go to the other concept in a train of thoughts contextually, right? That is very important because it kind of laid down the importance of relationships, how the things are connected. And the connections are a lot more important than the dots. So that was a very fundamental thing that he talked about. Later on, this ambient intelligence was very interesting. Gordon Bell talked about capturing all the data related to your life. And then there has been event web and exponential computing that a good friend of mine, Ramesh Jain, has talked about. And then relationship web and intelligence interface and so on and so forth. So there are a number of things that are there. Here's one slide that puts together a lot of things on what's happened on the web. We started with web of pages or web of documents, went to a web of databases, dynamically web pages, went to web of resources. We had services and mobile computing on the web. And then we have a web of people and a web of sensors, 40 billion sensors out there, social networks, user-created casual content, so much of it. And increasingly, we are going towards the case where web becomes an oracle. We ask questions and expect to get answers. And what you will see here is that one integrative way to think about this evolution is that you will see increasing use of semantics, an increasingly important role of semantics. It may have come, it may not be so obvious to you, but if you dig deep into that, you'll see that. And I'll show you some aspects of it. Some of the things are very clear to you. The use of statistics by search engine, the learning algorithms by search engines, for example. That's all very clear to you. What I'll show you is how adding a little bit of background knowledge of semantics makes them powerful and are expected to be the next generation of technologies coming from those search engines. And so what we also are seeing here is that we go from keywords to patterns, to objects, to now we are at the stage where we are able to understand events. Think about it. To you, after this talk is done, this whole thing is an amorphous thing as an event. Right? It's not a little single slide. It is not a single word. It's not a keyword that I'm going to talk that you're going to take with you so much. You might take some concept with you. And the event as a whole will be important. There may be parts of it you say, oh, he talked about sensor first, he's talked about social thing next. The components of that, that's what you'll do. Being able, for the machines to be able to recognize those things and then work with humans to help humans actually get to those events would be a lot more interesting, and that's what's going to happen. And eventually this will lead to enhanced experiences, technology that is assimilated in the life, right? And that's what I call computing for human experience. So to simplify, and being an educator, we have to be, we have to use some pedagogy. So get down to some core things. There are 4 enablers, as I put it. There's certainly a lot more than this, but these are the 4 things that I think we can concretely talk about. One is bridging of physical and cyber digital divide. So socio-technical systems and physical cyber systems, that's happening now, happening on a very large scale. Second is elevating the abstractions that machines and humans understand. So go from low level of signals and noise, everything that 40 billion sensors are producing, to something that I am interested in, something that can affect my daily life, something that may allow me to decide whether I should put on the coat today going out. Those are the things of interest. So you have to go from signals to observations to perceptions. That's one thing I'll talk about. I won't talk about the first thing much. Second would be social perceptions to semantics, because we are all interconnected. And this is very fundamental. The social networking thing is pretty significant. Whether you like Facebook or not is very secondary. Whether you use Twitter or not is rather secondary. But it is, in fact, changing the way we communicate, we keep in touch. And in fact, how we are starting to get news and information is increasingly being biased. Think about Iran elections and what the CNN anchor would say. We don't have our person on the ground, but this tweeter is saying that this thing happened there. Right? So this is the way we're changing even the news and the way we're getting information. And then semantics at extraordinary scale. You guys work at scale here, and there is a huge amount of issues and challenges in that area. But I think we have some, starting point on the understanding of how we can possibly do that. And I've laid down some of this in, there was a vision issue or internet predictions issue earlier this year, internet computing, and that issue we have a little blurb there. So physical cyber divide is narrowing, and here are many examples. One of the interesting one was is MIT's sixth sense thing, wearable computing, or more like gesture computing. What he says. So you have a camera here and projector, and you kind of do a gesture. And it says, oh, you try to take a photograph. It will take a photograph of you. Or you put a book there, and it will give you information from Amazon about that book. But one thing, once you look, this wonderful TED talk on that topic. One thing once you look at it, when I looked at it, that I started to think about it, is that as a surface technology, it's exciting, it's wonderful. I saw a huge promise of it. But I think what was still missing, at least for me, was how does that intelligence actually come? Where does that knowledge come? Where does you know exactly what you do behind it? Currently, they have been prototyped exactly for showing an exemplar. But how do you do on a normal scales, on a scalable scales, in a whole variety of situations? That is where the kind of things I'm going to talk about, I think, will play a role. There are many other things that are happening, Internet of Things, emotion sensors, variable sensors, body area networks. I was recently in Dublin and saw some wonderful new sensors that go on the body, sensors that go in the body, little sensors, these big sensors that gives you water quality things that I can take and communicates all the things on the by wireless network, and so on and so forth. Equally important to those sensor things is the sensors everywhere with human in the loop sensing. Because every time those observations are made, that human's knowledge, background knowledge, cultural biases, social, linguistic knowledge is all incorporated into what they are saying and what they are conveying. Using that, leveraging that is a huge opportunity for us. So there are a lot of things happening here. This is potpourri of stuff, and I have no intention of going through all of them. But that all objects, events, activities in the physical world have counterpart in the cyber world. That there's multifaceted context of real world captured in the cyber world through multi-level and citizen sensor participation. Each object, event, activity is represented with semantic annotation, so there is a common representation for each of them, XML, RDF, things of that nature. That for a chosen content with an ability to explicate and associate variety of relationship and events, so things are rich. They are not words, keywords. They are, by associating that keyword with a model, with a conceptual model, they become live, they become meaningful, right? That there is appropriate reasoning and human social interactions are available and applied. Insights are extracted. So there are things, and you can see the technological things in the current things there. The activities are anticipate, answers obtained, decision reached, communicated and applied. Many things of that kind that are happening. So let me take second of the four topics, elevating the abstractions that machine and humans understand. Signals to observational perception that lead to semantics, providing meaning and understanding of what's happening out there. Something that I should care about. People talk, people observe, people perceive, human perception, people communicate. We use language for that, cognition. So senses, cognition, language. Sensors do the same in a way, differently. Senses observe, perceptions, machine perceptions, communications. Increasingly, these are being meshed. And that's giving significant new power. Very exciting. And semantics for shared conceptual. So one of the things that also that is happening is that semantics, as I will briefly describe to you, improves, improves the perception across the machines and man. And semantics also helps with better communications. When the tweet comes with the semantics, I can better interpret what it means. What was the meaning that person had in mind? Because words, have, and I'll give you some very interesting examples of it as we go along. One of the infrastructural aspects is to be able to annotate every piece of content out there. So if satellite is passing me some data, I embed that, the temperature, I'm saying the temperature is in Fahrenheit. From there I can say whether that is hot or cold temperature. Remember, that's the transition I want to make. I don't care about temperature in particular Fahrenheit or particular centigrade. I care about whether it is hot, cold, warm, those kind of stuff. And same thing about location. And instead of vector thing, it says it's in Dayton. That's a very important thing. Instead of coordinates, that it is part of the Dayton. That is a lot more important to humans. And those transformations have to happen. And that happens through this lifting from the numbers and symbols to something that is meaningful to human. And that is done here is an example things. Here at NCSA, you also have worked on something along this line, but here you have sensor data. We are part of a W3C semantic web networking group that I co-chair, and that one of the things is development of sensor ontology so that you can deal with the heterogeneity of sensors. Other is how do you annotate them with regards to the models or ontologies out there. So you can model, saying that this little thing here in XML is that thing that. Or, for example, here is another content. I can put here in the domain ontology person and company. I can mark up that it has particular spatial or coordinates and coordinate systems, or that it is temporal thing, time unit, time zone, variety of things of that nature. So a document may have all these little terms, but don't think of it as keywords. Don't think about it as numbers, and don't expect your computer programs to understand those things. Instead, bring them at a level of high level of abstraction so you can talk about things that we really care about. And Corey is here. He kind of coordinates our semantic sensor network web project. He developed this thing here, takes a lot of data of different kind, and it's in a web infrastructure, adds semantics to the services layer, and allows you to do more complex query about that and do the mashup and so on and so forth. So to give you a demo, for example, of what that looks like and why that is significant, is this little demo here. Well, it's not entirely little. Let's see. Yeah. So in this demonstration, actually it's live system, so you can actually play with it. It's not just can demo. There are 20,000 plus sensors from MesoWest, a network that we tap into, and each of those sensors are accessible as service and as a semantic version of the service. So there's semantic description of where the sensor is, what kind of data it reports, things of that nature that can be done at high level abstractions. And that then once you have that data, what is interesting is the following. You're doing, using ontological knowledge and rules, you infer complex weather conditions from simple sensor readings. That is the power, right? So as I said, you would care that on a particular day in Illinois, was there a blizzard? That's something that you'll be interested in, right? So here, let me just go, I won't go into detail, but here there are a lot of phenomena or a variety of sensor data but what is more important is what you can compute with that. You can compute freezing rain, windstorm, snow flurries, blizzard. These are the things that require data from multiple sensors. Blizzard requires you to say that there is precipitation, there is certain wind speed, minimum wind speed, and maximum visibility. These are the things that are conditions for defining a blizzard, right? And so what you want is the user to be able to simply say, now this location on this time frame, so I select the, there is something about trust here, I won't go into that, belief and trust, and we do work on trust in sensor and social data, very interesting topic. I know that you guys are also quite interested in security, we also do some work on security, I won't talk about it today. But in this time and this location, there goes. There are a couple of, you see those dots came up. So this is where there was blizzard on those days. And you can pull up the data and you can say why it was blizzard, what are the data they're supporting, so on and so forth. And you're going through, freezing rain. Of course, there are many freezing rain conditions on that day throughout the country, and so you can look up all those things like that. And there's KML and the standard languages and so on and so forth. So another version of this demo, which I won't show you, uses link open data, where it has geonames. And so what happens is that you map your coordinates to the geonames so that you can now talk about, give me the, basically it allows you to do this thing now. I say, give me the latest sensor reading from the nearest sensor. And it will also says, give me something from Urbana. And Urbana is mapped into location and so on and so forth. So if you Google semantic sensor web and then go to things, there are about 5-6 demos, and that can also show you that. So Let's go to something more interesting, and again this is something that Cody is working on, active perception or perception cycle, whereby I show the role of ontologies in background knowledge for situational awareness. Again, situational awareness for decision making, this is what humans talk about and care about. So what we want to do is to enable situation on the web, we must utilize abstractions capable of representing observations and perceptions generated by people and machines. People observe, machines observe, then they perceive, and we understand the events that matter to us. So in a sensor and observation ontology, I could take observation and identify a particular quality on which I can do computation, right? So your quality of redness, I see something that is red. And then humans and machines have different perception mechanisms, but through inference we recognize what that entity could be. And there is something here, that process, and that is described in what Corey calls perception ontology. So there is a recognition that there's entity, red apple there, and that you have this background knowledge such as the apples are red, which is important for you to come to that conclusion. So there is role of domain ontology that says fruits and their colors and so on and so forth, that is applied. This is a very generic principle. Now think how all that comes together. And other thing is that because there are billions and trillions of observations, how can I effectively create a computational environment, a reasoning environment, whereby I would actively seek out the observations that will help me understand a high level phenomena or understanding of an event. That is the perception cycle. Okay, so the perceiver sense of focus. We humans are great at it. A fly is going there, and suddenly we recognize from the side and we focus on it, right? Machines, how can we get machines to do that also, right? From all these billions of observations. And so to actually seek out what would allow you, what observation will allow you to satisfy a particular theory or understanding of a situation is an important challenge. So you ask for it and you get the thing back. So this is called perception cycle or active perception. And these are the players, your observers, quality, entity, perceivers, and so on and so forth. Let's look at an example. So the new thing is, in this whole thing, how do you effectively use background knowledge ontologies that are all increasingly available, that are, you don't have to necessarily devise all of this for yourself, and use those knowledge on a web scale. So this shows you weather ontology, a domain ontology, right? You have quality and entities, and so blizzard, and the things that participate in defining blizzard is freezing temperature, and here snow precipitation, and here high wind speed. These are the things that are qualities that define or make for a blizzard, for example. So here you have a possible so-called perceptual theory, possible weather phenomena that may be out there, and you want to decide which one is something that is happening at some location. You have obviously the sensor observation ontology, you have perception ontology, and perceiver asks, saying, well, give me something about wind speed because I observed something of interest to you. So it got somehow some seed information. With that, you ask for wind speed, you get high wind speed, and with that, you rule out several possibilities, and then you say, okay, well then precipitation is the next thing on my agenda. Get precipitation, snow precipitation, and once you get that, you can now, with other thing, you can say this is blizzard. Right? And you are trying to reach that and do that in a very scalable manner, and very scalable, both semantically scalable and computationally scalable. In this particular case, you have ontology, sensor observation ontology, you have domain ontology, many of are developed by communities, for example, and you have perception ontology that we have developed. And there is this perception cycle, and also there are issues of trust. When can I start believing on these observations? And what I will talk about is, again, there's a variety of things about data coming and beta distribution, and when the thing you start to really believe in. But what's happening next is that you have trillions of observations, trillions plus of observations from human body. This is body area networks and sensors on the body and other things we were talking about earlier today. Also all the stuff outside. surrounding the human, right? So all those things there. And I want to find out what's meaning to human experience, right? So let us look at that, a little demo here. So this one essentially takes some weather data from US, and you can see here the legend, the variety of things there, clear, rainstorm, rain showers, flurry, blizzard, those kind of stuff there. And there is a huge amount of data that are coming, streaming data that are coming from the sensor, let's say. We're also working on streaming data, so doing this on the runtime, on the fly. And then this thing, the height shows the trust value here, and that the color shows what it has found. And you'll see that at some point of time, there are all the conditions that qualify and say, okay, there is some part that is blizzard. And so there are a lot of interesting things you can do with these things, and you can do roughly on a scalable matter. So the storm is kind of moving through the system. Going, just focusing here. So you can see, I'll just go faster, so you can see the red part is the blizzard part, and you can look up the details of that. So that there's some place that condition was. You can look up the actual data also, and so on and so forth. All right. So something you kind of get an idea of that. There is a okay. That's probably enough for now. Let me switch the topic now to human in the loop sensing, or what I call citizen sensing. So this place, if you don't know, it's Mumbai, India. And November 26, 2008, War on Civilization, terrorist event, and this started coming up on Flickr. Vinu was a student, Columbia student visiting Mumbai at that point of time. From his mobile, started uploading, and I was glued to Twitter, and I saw this thing coming on the tweets. This is how we got all the stories. So the world saw through the eyes of people, and the world read through the words of the people. People told the stories to people, right? And so what happened was a new dissemination phenomena, whereby global network of citizens or citizen sensors are observing, perceiving, transmitting, and reporting. Right? So we'll talk about social perceptions, observations, and semantic sense making. There are varied perceptions that lend to varied observations. For example, in the US healthcare debate, these are some of the places where there are enough number of tweets for me to do statistical and textual analysis of tweets coming from those locations. And it allows me, say, from Seattle or Washington rather, I find these sort of tweets. I think, and you can see what are they interested in: life counseling, faith-based groups, things of that nature. Right, and you can what is on their mind, it kind of cults out, it bubbles up. But on the same day, you go to Florida and you get things like Soylent Green, and I'll soon talk to you, show you what is the context of Soylent Green there. So there are social components of content that also, but this is not that simple. It's not purely text processing. There's textual content, lateral cloud statistics from content, there's spatial and temporal parameters, so where and when messages originated, the postal demographics, age, gender, socioeconomic status, the twin text and the terms and so on and so forth. There are other things, what else happened near these events, what happened before and after, what caused these events, their spatial views, tweets originated near this location, during that time, an intersection of that, saying tweets originated between time and that time, and so things of that nature. Here is a very interesting thing. There's too many things to talk about, so I'll give you some sample of it. See, on the left-hand side is the basic TF-IDF analysis, and that it shows, it says Mumbai is the highest, most important concept. Well, really, that's not conveying much at all. But foreign relations, for example, is more interesting. It's the impact of this terrorist event on foreign relationship. That's pretty interesting. So when you do spatiotemporal thematic score bias on those things, so when you enhance these traditional techniques with those biases, then you get a different perception here. And for example, foreign relations comes up much higher, right? So these are some of the interesting things. So let me show you Twitteris very briefly. This is our attempt to help you to help keep up with citizen obsession on Twitter, what people are talking about, where and when, and put citizen reports in the context of you by overlaying with news, Wikipedia, video, audio, and so on and so forth. Let's look at a very brief.
Exactly this. Bring all the information back. It is the ability to go beyond simply showing.
So let's. And Twitteris, that was the earlier version of Twitteris, and it's growing, and we have number of things. For example, if you take Austin plane attack, let's say, and then what you'll see the related tweets on images and video come about. I'll pick a particular thing here, and you can see very interesting things. For example, a Billy Ellie band comes up, and quickly gets you to. Suppose I pick that. Then these are tweets related to that. Then Wikipedia news items. From that news items, we extract the entities of relevance that are relevant to that event. Very quickly, we get there's Joe Stack, the guy who actually flew the plane, kind of stuff. And you bring up related video very quickly, and kind of see a whole bunch of stuff about that, or you can see the F-16 that just scrambled moment after that. So all this kind of information there, you can see the volume of traffic, you can see this is a very interesting one, and this is going to dynamically build an entity relationship graph. So all the things that are being connected. Now this is where we can use supercomputer because the analysis is trying to do on the fly. It's a bit slow. It's not that terribly so, I guess, not too bad, but you can see it's kind of growing. It will show and start connecting the stuff and see what one thing led to another, and you can kind of study the whole event folding in time and space, and by people and location and organizations and things of that nature. And remember, all these entities are also sort of semanticized, meaning we know that it's not a keyword. It's we know it's a name of a person. We know it's the name of an organization. So all that knowledge is out there because of the background ontology. So the things you get is a lot more meaningful here. than just sort of words and statistics about the words and so on and so forth. Soon to be released, sometime this week, I think, sentiment analysis, intention analysis, things of that nature. So there are a lot of interesting things happening in this space. And the things can't be textual. For example, there are many things. Understanding casual text is rather challenging. So Meena Nagarajan, who did she completed the PhD thesis this summer. She's now at IBM Almaden as a research staff, and her work was on understanding the informal text or casual text, and she did on NER, name entity recognition, and many other things along that line. But see, for example, here is a system on the web, and it tells you the temperature, what kind of weather there is based on tweet analysis. But unfortunately, there are tweets here of the kind which says that now playing Adam country shine on CRBN. Clearly, that site takes sunshine as the weather information, which it is not. So obviously, keyword kind of thing would get you nowhere. Using domain now, so what is the secret sauce? One of the things why we can do some of the interesting thing is that we supplement the statistical NLP and the machine learning techniques using background knowledge. Here is an example. See, there may be occurrence of words like Evas or Kuzestan, things of that nature, right? But if there are one or two random tweets from one location, what can you make out of it? Nothing. But what if I had a domain knowledge that, we have done work on spatial aggregation, things of the nature, and this model is built automatically, dynamically. Actually, I'll come to that briefly later on. That I can say that, oh, these are all in the same region. Now I can collect all of them. Now I have statistics by a region defined by culture or politics or geography or whatever you want, and I can analyze them. Now that makes for a lot more sense. If you want to go to another domain, not social domain, but other domain, what do you say? Let me focus on only the non-flat terrain. See, that kind of stuff is very important, and being able to reason about that very quickly and aggregate signals or sense observations dynamically would be very powerful. There's more than that. Obviously, you know that this is a part of this town is part of this county, or that gives you a lot of other things. Information. Here's an interesting example. Keep your smile on, or got your new album Smile, loved it. What is it? Which one is a music mention? Which one is normal, human emotion? Or there is mention of Nariman there. What is Nariman? How can I make sense of it? So in this case, with Nariman, for example, I take the metadata embedded in those things, geocoding, reverse geocoding, databases. And there is there's a building called Nariman House, where there was a Jewish house of worship there, and that is what struck. And then now I can make a sense. Oh, Nariman here is that. Here, this thing here about word sour. Oh, these sour times, rock. How do you make sense of it? Here we applied music brains ontology. Or a data set. This is web of data or link open data. This is public. 500,000 plus artists are already cataloged there. I am leveraging that. I'm just using that. And so there's our times there. It's taking our time. I have good reason with other information that this refers to that track. Sour times. That gives me a lot more meaning than some text sour times. Right? So here's another very interesting one. Opinion expression. Your new album is wicked. What does it mean? What is the emotion that happens? Well, it so happens that there's something called Urban Dictionary. It tells you in US what wicked means, in UK what wicked means, in France what wicked means. And now, based on where the tweet came from, I can tell you what it means. Right? A lot more exciting. So, applying the knowledge of whole variety, by the way, I showed you the dictionary, I showed you music brains. We have developed a lot of formal ontologies and in biomedical domains in particular, health domains, and you can apply that, and that's what we use too. There are other interesting stuff related to that I won't discuss because of the limited time here. But for example, traditionally when you process messages, you first do spam detection and throw away that thing. Here we found that it will be more interesting to do first, in at least the music popularity application, not to do spam detection first, but actually do NER first and then do spam detection. So this is soil and green example where you got a lot of background information to understand the relevance of soil and green in the context of healthcare reform. And these are the kind of things that we are working on now: people, content, network analysis, sentiment, intention, cultural and behavioral knowledge, modeling, and information diffusion, influence spreading, group formulation, and so on and so forth. And you can merge sensor and social data. So there is this image up from the sky at different levels. There is this photograph. There is this tweet. I can bring them all together and I can do mashup with geographical knowledge as the background. So I find the 9 locations where the terrorist struck, and I can show you each of the places and the order this thing occurred and what are the things said about each of the locations. That makes for a lot more meaningful thing. The another interesting thing we work on is continuous semantics. A lot of things are on the fly. So increasingly popular social, mobile, and sensor webs exhibit characters like spontaneous. You lie, President. That thing. Within half an hour, there was an article on Wikipedia, which had quite a bit of background about Joe Wilson and other things. Helpful, available to me to leverage to understand tweets about you lie event, as an example. Follow a period of rapid evolution involving real-time or near-real terror requires continuous searching and analysis. Haiti earthquake, and many of those things, crisis management, emergency management things. Many distributed participants with fragmented and opinionated information. Red and blue states, and conservative and Tea Party, and so on and so forth. Accommodate diverse viewpoint involving topical and contentious subjects, and feature context colored by local knowledge as well as perception based on different observations and their sociocultural analysis. So there are many of those things. So we have this so-called knowledge life on the web, and you can get background knowledge, physical and scientific principle, historical facts, content created by humans, and through social processes. And you can leverage that. You can use that in information and knowledge extraction, like understanding WCAG. And then you can use that in discourse and analysis, and of variety of kind, or situational awareness. So there are many static domains, like and where we have developed large ontologies in biomedical domains. That is an example. Then there are community maintained knowledge bases and dictionaries, MusicBrainz, IMDb. And then there are rapidly evolving domains, and you have to create, can you create models for them in a socially scalable manner, as I might say. And here, to grow this organically and without minimal human involvement. So we have worked on knowledge extraction by crowdsourcing. These were the terms that our biological colleague gave from Air Force Research Lab. And from that, we automatically created this, by mining Wikipedia, a high-level approximate model. And that model looks something like this. And this is a pretty interesting model. You'll see interesting relationship. Disease as associated anatomic site. A pretty interesting relationship being extracted. Right? So it's not just some hierarchy or taxonomy. There is actually a rich conceptual model with name relationships. Then what we do is, once we have this model, we backfill it using focus extraction on biomedical text. So there's a lot of work on biomedical text extraction, name entity, and relationship extraction biomedicine. We have our own work in that area, and we essentially complete this model with those facts to create an ontology. This is an example. Earlier I showed you of that, and it shows how the different tweets can be linked to each other. But these models were created dynamically, automatically through mining Wikipedia. And then you can create this ecosystem. So you have these tweets, and these tweets are processed through systems like Twitteris that I showed you, and I get this kind of key phrase cloud, and I apply the domain model that allows me to understand what these things are much better and how things are related, and say what are the tweets from the same geographical area or cultural area or things of nature. And from then I can do more sophisticated ways of filtering and focusing tweets to get another set of tweaks and continue the analysis. So there is a continuous analysis of real-time data that I can do and understand how situation evolves. So significant capabilities that will come will be richer forms of relationships. I call relationships at the heart of semantics. Richer support for events and situations, and significant advance in semantics and knowledge and this linking of cyber-physical and socio-technical systems. So one of the things is that a whole bunch of relationships that makes for rich things. So here is my student at former student at Google, I/O event, but it's all the things connected, and this connection is what is important. This is what whenever Bush had in mind, with meaningful traversal of things and connecting. So creating this thing dynamically, I call it relationship web, and that's very interesting. Look at this. This is very interesting. Iran election, for example. The election as a whole occurred over a period of time. You call it an event or a situation, but within them, all these different events, sub-events occurred. And they're very interesting. For example, NEDA's killing of the NEDA, for example. Very, very important, powerful event, that characterized that whole situation. And so on and so forth. So when you want to understand this thing, you want to be able to isolate each of those things and play to the human. That's where this understanding comes in. So to kind of wrap it up, more or less, we have a whole variety of data. You have a structured databases, relational databases, RDF, and so on and so forth. You have semi-structured data, XML. You have textual data of whole variety of things. We have done extensive work with the social data, in biomedical data, and the health informatics data in the textual part of it. We have done a lot of experimental data, for example, mass spectroscopy data, or RT-PCR, or NMR. These are the kind of things. So we deal with those kind of data. Multimedia and social data, multimedia content and other web data, sensor data, whole variety of sensor data. We also have some intelligence and defense related applications. And we use domain models and created ones that are created by the community, ones that are created by experts, committees, and dynamically, automatically created and harvested. Right? So a whole variety of ways you can create these models, and that's why I didn't call them ontologies alone. And with that, we do semantic metadata extraction, and you get semantic, so you kind of get something in technological terms. You get RDF. From that, you can compute paths. You can get subgraphs of interest. So a lot of interesting patterns you can analyze. But beyond patterns, you can go with inferencing and reasoning, depending again on the formality of the representation, or formalness of the representations, and so on and so forth. And I'm a big believer on combining there's a paper that we written called Semantics for the Semantics Web, the implicit, the formal, and the powerful. And so, the implicit is more with learning and statistical analysis, for example, statistical NLP and those things. And you can make that powerful using ontologies, for example, or domain knowledge. Formal is obviously I can do, palette reasoning or, any of the description, logic-based reasoning kind of stuff. And then powerful, I have to use probabilistics and possibilistic and those kind of techniques and fuzzy stuff to make the sense of it. With that, we can develop very advanced applications, semantic search, information, semantic integration, analysis, discovery, question answering, institutional awareness. So let me end with, again, this kind of scenario that I started this kind of work with. Sensor observe environmental phenomena and nearby vegetation. Observation analysis determines potential situation and effects. Through this reasoning or perception cycle, we perceive possible storm as the best explanation of hypothesis and of observed phenomena. And through deductive reasoning, we can decide who can get affected. That this, there will be possibly, rain carrying salty water, and and salt carried over the wind, over the ocean, and that can affect the crop. So then to alert, to alert the farmer that there is something coming that you should take care of, farmer goes out, looks in the sky or gets other supporting data, gathers children and or neighbors, and tries to take the solution like this. If it's a soil of this type, do this, soil of other type, do something else, and saves the crop. But that's kind of the natural ecosystem on which we want to be part of, in which we want to influence, we improve that whole process and such. A lot more happening at the Noesis Center. Number of demos are there. Here are just my immediate part of things, some of my students, and some influential work, they are there. And these are some of the topics that we recently talked about and that we work on at a key level, key phrase term in the center. So they span from semantics for things at human level to clouds and services and social data and sensor data and so on and so forth. Okay, so that's my talk, and this time I'm more than happy to take questions or comments.
In scientific computing, I see a really strong analogy between the perception cycle you're talking about and the hypothesis testing cycle that scientists engage in. And if you consider science writ large, there's a kind of situational awareness that science provides to us. We've been doing scientific computing for a long time here at NCSA. We have a bunch of existing techniques that we continue to use successfully. We build domain-specific codes and assist in running them. We use object-oriented programming, we use relational databases, we use batch processing on HPC. And so I have a couple of big questions as somebody who's worked in the semantic field. What do you think needs to happen to the kinds of techniques that we use to build scientific computing in terms of, for instance, object-oriented programming? What needs to happen to our programming models, batch HPC, what has to happen to HPC to begin to support the faster cycle and the kind of semantic services that you're using to power all of this interesting stuff?
Very good question. I have a two-part answer there. What needs to happen at both bottom-up and top-down? Let me say bottom-up first. One of the things that we did as an exemplar is that we are working on complex carbohydrates and role of some enzymes in cancer and such, and not my collaborators. And that they were doing mass spectroscopy, and they had a large workflow. And they would produce 500 files actually in a single run, and 5 gigabyte of data or so. And the postdoc would work on 7 computers and physically transfer the files and so on and so forth. Now, not only we completely automated that, but we embedded provenance at each step of the process. At the end of the day, they would be able to manage this workflow at a as a scientific workflow and kind of thing. And that is kind of thing I'm sure you have also done here, and a lot of other people have done. What is more interesting is that the provenance information in a semantic form, meaning what kind of object are recognized, what kind of cell line or culture or particular machine description and the settings and parameters and so on and so forth, all described at an ontological level. We have N-glycosyl, we have proprio ontology, 500 classes, 3 million instances. That's a very significant ontology that we developed, is public, and is through NCBO, National Center for Biomedical Ontologies. That is used to embed provenance metadata at every stage of the way. Now, what that does is then the scientists at the end can ask questions: where did this data come from? This is something they would have to go to lab notes, and they may not, if they don't have metadata, they won't be able to reuse the data. Not only that, but because of, if there is a deep provenance and formally encoded, then you can reuse the data, because somebody else can integrate data from multiple experiments. Typically in science, everybody repeats the experiments. They don't share. I mean, they share after they publish. And then there's no incentive to manage the sharing of that also. Centers like NCA can, in a large funded project, can support through a particular life cycle, but beyond that, nothing much happens. So, but what if there was a provenance all the way, and then you knew exactly the condition in which data was created, manipulated, processed, and so on and so forth? Now the ability, the quality, now ability to use the data is significantly improved, as an example. Secondary use of data is significantly improved. So in one sense, and I can go on, but to keep the answer short, one is the bottom-up process where in the fundamental process of creating the data and manipulation itself, we can embed semantics. That's one thing. Second is that we have to make these tools usable by scientists, make it very easy. Now, here is a very good example. Dr. Tartan, he has Center for Topical Disease, and he's my partner. I have an NIH R01 that I have with University of Georgia and Stanford. And he used to have an IT guy who would write SQL queries on the data that have been curated and put into relational database. That guy has left. He can no longer actually do those queries. His postdoc is a biologist. He doesn't want to do any of these things. We, in this collaborative project, have developed a system called QB, where we have developed parasite life cycle and parasite experiment ontology. And in ontology-guided manner, just like using, because it's AJAX interface, so just like using Google, you take concepts from ontology and create the query. And the Sparkle query is automatically created, and he gets data not only in a list that you will get, but actually nice multimedia of different form of, abundance of a particular occurrence in a particular lifestyle stage, all those kind of stuff. So they are able to now do these queries, rather complex queries, with 20, 30, 40 variables, and you won't be able to write in Sparkle. Most people won't be able to do that. Instead, on the the biologists themselves can do that. But this is a very good example of collaborations where we are very motivated to make them successful and have actually given them the tools that they are able to use. And that is what needs to be to happen. I think it can be done because I've seen the examples of that. The rest are non-technical issues like how the funding goes or how people work together and those kind of stuff.